Alright, so just moving straight on from previous session. So you can solve for your lambda star and you'll get this value. Now do something similar. Now differentiate the expression for bracket gamma gamma. Differentiate now with respect to lambda star, and you will get this. Okay, pretty straightforward. And therefore lambda at the minimum value gives you this expression. Okay, so you've got this lambda star at the minimum value of bracket gamma gamma is this. You've got a similar expression for lambda at the minimum value. That's this. Okay. Now take these two, the lambda min star and the lambda min, and pop them into your expression for bracket gamma gamma, which was well. Let's see. You had a. I don't think. Yeah, you can't see it. Well, yeah. Go back to the previous session. Have a look. Now plug in this value for lambda star. Plug in this value for lambda, just lambda, and you'll find. So this beta beta bracket cancels with this one. And you got a minus here, you got a plus here. So beta alpha over beta 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 alpha beta alpha beta. So this is the same as this. So big bar cancel, these two just cancel out, and you're just left with this one, right? So this plus, well actually minus this is greater or equal to 0. Okay, bring this over to the right hand side. So then you've got bracket alpha alpha times bracket beta beta is greater or equal to bracket alpha beta times bracket beta alpha. Right? Now, can you remember from a few sessions back that if you take a bracket and you conjugate it, you star it, the result you get is the same as if you just reverse the bra and ket. Like if you have bracket alpha beta and then you star it, you conjugate it, you will get the bracket of beta alpha. Okay? So if for example, if I star alpha beta, bracket of alpha beta, I will get beta alpha. Right? So in other words, reversing that logic, I can rewrite this beta alpha as alpha beta star. Okay. Well, now I've got something times itself starred. So that is this here is the same thing as the modulus, the absolute value in real number, the absolute value of bracket a alpha beta squared, right? And there it is. There it is. There's your final result. There's the end of proof of the Schwarz, which in the German word means black, the color black, Schwarz inequality. And I've written here QED. That's the old-fashioned way of saying end of proof. It's from Latin, and Latin's not used much anymore. It's a dead language. So, but QED means, well, the actual Latin is, I don't know Latin, I just know bits of it. Quod, which means what, erat, what was to be demonstratum, what as was to be proved, as was to be demonstrated or showed or proved, as was to be proved. And it's used here as an end of proof marker. Now, so that's the old-fashioned way of doing that, indicating to the reader in a book that you've come to the end of the proof, QED. Now, in modern terms, so again, AKA, also known as, or well, it's not really it's an alternative use for the same concept. In other words, an end of proof marker is like either a hollow square or a hollow vertical rectangle, sort of like this vertical rectangle. This end of proof marker, the last couple of years is pretty well standardized now, I notice, in many mathematics textbooks, because it's useful to know where a proof ends. If you have a lot of discussion involving lots of mathematical reasoning and symbols and so forth, if you're reading some topic for the first time, it is not clear when you're reading the text where the proof ends. So it's useful, this end of proof symbol, a marker telling you, at the end of this line, that's the end of the proof. It's useful to have. So often a hollow vertical rectangle, like this. Okay, right. Okay, so now we've got our stepping stone done. We've got our lemma proved, our preliminary result, which is Schwarz's inequality, which is this, right? And we will use this now in the bigger work, the main result, the main proof, the main theorem. And here it is here. Now we've covered fairly well the usual undergrad textbook level Heisenberg uncertainty principle, HUP. So what I'll explain this in a minute, but here you have the statement of the generalized Heisenberg uncertainty principle, and it's between any two incompatibles, so you cannot measure both of them to infinite accuracy simultaneously, right? They're incompatible. And two general observables, just A and B. So you're defining, here you've got the sigma, so we were talking in the previous session, this sigma now is interpreted to be a standard deviation, right? A statistical standard deviation. Now I've got the square of it, so we're talking about the variance. Okay, so in other words, you do a whole bunch of measurements on A and a whole bunch of measurements on B. You get all the different results. So you find the variance, in statistical terms, you find the variance of your A measurements, and you find the variance of the measurement values for observable B. Okay, the variance. And then you multiply these two variances. So you get sigma A squared times sigma B squared is greater or equal to the square of the whole thing. So it's 1 over 2i. And then notice these angular brackets here. So we're talking about the expectation value. In other words, the average value of, right? Of what? Well, the commutator of A hat and B hat. Remember, A hat and B hat, they're the corresponding operators of these variables, A and B. And that operator you use in this variable's eigenequation. Right? That's how you go about finding the allowed measured or measurable values, the eigenvalues. Right? Okay, so it's the square of this whole thing, so 1 over 2i, angular brackets, so expectation value of, or the mean value of, the average value of, the commutator of A hat and B hat. Right? Now